Okay, I'm sorry, I think I was on mute. You can hear me again, right? Okay. Yes, exactly. So it's hectic for people who are taking both fast waivers and the crash course this week. For this week, it's a bit hectic. That includes me, who's teaching both of them. This week has been like insane. There's hardly any time to sleep. So I was saying tomorrow is not the last day. So bad news. Tomorrow is not the last day for the S1 class. We will need a couple of more classes. We will be done in terms of concepts, inshallah, but we will need a couple of more practice classes, because in representation of data, we have linear transformation. We have linear transformation that's left, and we have the diagrams there: cumulative frequency curve, histogram, box inverse, time and leaf. Although they're easier concepts generally, but we haven't practiced them at all. So we might need a couple of classes for practicing representation of data as well. Maybe one more class. We will try to complete the concepts tomorrow, and then another class in which we do practice questions on representation of data in particular. So I'm thinking of Friday. So Friday might be the last one, and then after that, it will depend on you guys. If you think you need another session to maybe practice any other specific questions that you guys have, either from normal distribution or from representation of data, we could have that other class as well. But Friday, at least, is going to be added as an extra S1 class. For M1, we don't need that. We won't need that. But for S1, we will need at least one more session so that we can do some more practice. Okay. So not tomorrow. Keep Friday in mind for that. All right. Okay. So now today, what we want to do is we want to do some practice questions on normal distribution and some past paper questions on normal distribution. And in addition to that, we also want to do binomial to normal approximation, inshallah. Okay, that's what I'm planning for today. So let's get started. Let's start with some questions on normal distribution. If you guys have any specific questions, you can let me know. We will start with them. So you're saying question 37, first of all. What I'll do is I'll start from that, and then we'll take it from there. Normal distribution. Okay, so what have we done until now in normal distribution? We said we would be finding probabilities using this normal distribution curve. The area under the graph represents probability. And to find the area under the graph, what we do is we use a table that's called the normal distribution table. We have learned how to read the table both in the normal direction where we have the z value and we find probability, and also in the opposite direction where we have probability and we have to find the z value. We know how to do that. Then there are two types of problems that we have done until now. One is where you have some data given, you have the mean given, you have the variance given, and you are supposed to find some probability. Okay, so x greater than something, x less than something, or x between two values. How do we do that? Whatever value we're given in terms of x, the first thing we always do is we convert that to z using this formula: z equals x minus mu over sigma. And then we have to use the table to find the probability. But the table requires the probability to be in this format, that z has to be less than some positive number. Then you can find that probability. So table only gives you area to the left of a positive number. If it's not that format, you have to convert it to this format first before the table. Okay, so if it's any other format, you have to convert it to this format. And then you use the table to find the probability. Okay, this is the easier type of problem that you see. This is one possibility. And then in the last session, we covered inverse normal. What is inverse normal? Inverse normal, what happens is you have some probability given. So the probability will be given. And you'll have some information, some data missing in that question. So you might have the mean missing, you might have standard deviation missing, or you might have the value of x missing, which you will have to find out by using normal distribution in the opposite order. We call this inverse norm. Now, what's the process for that? The process for this was that we would, first of all, figure out if the z value is positive or negative. So whatever is x value, for example, if it's x less than something, less than 19, what we do is we first of all write it as like this z less than some number. And then we have to figure out if this number is positive or negative. That's the most important thing in inverse normal. You have to figure out if that number is positive or negative. Okay. Once you figure that out, then you convert it to the standard form. If it's positive and it's already less than sign, then that's work. You can go to the table and find that z value. If it's not that form, you have to convert it to this form. First of all, then you use the table to find the z value. And then you put the relevant sign with that, positive or negative, depending on what you found in the first step, whether that's positive or negative. You put that sign with that, and then you use the formula z equals x minus mu over sigma to find those unknowns that you have. It could be the value of x that is unknown. It could be the value of mean that's not known, or it could be the value of standard deviation that's missing. So you'll find that using that at the end, right? That's what we have done roughly in the last couple of sessions. Now today, primarily, I want to do some practice questions, and then we will be doing binomial to normal approximation afterwards as well. Let's start with this question that you're saying. Question number, so it's not about approximation, right? It's not about approximation. Yeah, it's not. Okay, so let's have a look at this. Question number 37 from the worksheet. Let's try this. Okay, so it says the time spent by people visiting a certain dentist are independent and normally distributed with a mean of 8.2 minutes and standard deviation is not given. 79% of people who visit this dentist have visits lasting less than 10 minutes. 79% of people have visits that last less than 10 minutes. That's what we're given. And what we have to do is we have to find the standard deviation for this data. So the probability is given. What probability is given? 79%, right? So percentage can be thought of as probability as well. We can say there's a 0.79 probability that if you were to choose of someone randomly, they would have visits lasting less than 10 minutes. So what's the variable, first of all? Time spent, right? That's the variable. This x. This is the. They're saying this is normally distributed. So x is normally distributed. Its mean is given to be 8.2, and we are given probability of the time being less than 10. Probability of x being less than 10. What's that? That is 79%. We can say that's 0.79. That's what we're given. So probability is given, and what we have to find out is what the standard deviation is. So this is inverse normal, right? We have probability given, and data is missing. How do we follow this process now? The first thing we do is we write this probability in terms of z. So we say, okay, x is less than 10. What about corresponding z? It would be z less than some number, and that's what we need to figure out. That is 0.79. And now we need to first of all think of whether the z value is positive or negative, because if it's positive value, then you can use the table directly. If it's not positive, you have to convert it to the standard form. The standard form looks like this. probability of z less than a positive number, right? That's the standard form that we've got. Now, what does the normal distribution curve look like? This is roughly what the curve looks like. Okay. This is what the normal distribution curve looks like. Now, we are saying this value towards the left side of this value, we have 0.79 area. Now, is that a big area or a small area? You compare it with 0.5, this area is bigger than 0.5. Okay. So now you want to place z somewhere such that the area to the left side of that would be greater than 0.5. If we place z here on the negative side, what's the area to the left of that? That's smaller area. If we place z on the positive side, then the area to the left of it, that is now bigger than 0.5. And that tells us that this value has to be positive. Okay, now if this is positive, that means this is standard form now, z less than a positive number. So we can use the table directly. It's the standard area. This is given in the table directly. We can just you go to the table, find the z value corresponding to 0.79 probability. We don't have to convert anything. We don't have to change anything in this case. So let's go to the table and look for this probability 0.79. Remember, the probability is 0.79. It's not the z value that we're looking for. Probability is 0.79. So 0.7900. Let's search for that. 7979. Where is that going to be? Okay. This is the value that's immediately smaller than that. 7881. This would be bigger. So we take the smaller number. Z value is 0.80. And then how much do we have to it at the end? 19. Right? This is 19. What do we get here? 7. So the z value therefore corresponding to this is 0.807. That's what we use here. Okay. So this gives us the z value as 0.807. Now, if this is the z value, what we can do now is we know that this is a positive value, right? So we just leave it like this, put it in the formula, z equals x minus mu over sigma. Z is 0.807. In place of x, we can put 10. Mean is 8.2 divided by standard deviation. And you can find the standard deviation from this. What's the value of standard deviation? What standard deviation do we get? It's not 0.807. Maybe I might have done something wrong. 0.79. 0.79. 0.807. Oh, that seems to be correct. Okay, should I just explain that again? So probability is 0.7900, right? So what we do is we search for that probability here. 0.79, we search for that in this region. Okay. It's going to be between these two values. What we do is we take the smaller value, smaller of the two numbers. 79 is going to be in the middle here, right? Somewhere between these two numbers, between 7.7881 and 7910. We take the smaller of these two numbers. We take 7881. What's the z value corresponding to that? 0.8 and 0. Right? That's the first two decimals. And then you wanted 7900. What the value that you're getting there is 7881. How much? What's the difference between these two? 19. You need to add 19 more at the end so that the total becomes 0.7900. This is 19. What's the third decimal place that you get from this? That's 7. So it's 807. Is that okay? Okay, all right. So you don't have to look at z. You have to look at probability in this case, right? Probability is 0.79. You go back and find the z value from that. So standard deviation, you're telling me that turns out to be 2.23, and that's your final answer. That's what we had to do in the first part. Okay. Fairly straightforward. That's an easy inverse normal question, the first part. Now it says find the probability. So now we're looking for probability that the time spent visiting this dentist by a randomly chosen person deviates from the mean by more than 1 minute. Okay, how do we think about this? Time spent deviates from the mean by more than 1 minute. What's the mean? Mean is 8.2. Now understand the question statement correctly. 8.2 is the mean. 8.2 is going to be exactly in the middle, right? That's the mean. Deviation from the mean should be more than 1 minute. Deviation means distance from the mean. Now, on the right side, if you do +1, you get 9.2. If you do -1, you get 7.2. With 7.2 and 9.2, the deviation would be exactly 1. We want the deviation to be more than 1. It could be on both sides. It could be on the left side as well, not just the right side. So you could have a probability. You could have the time greater than 9.2. In that case, it would be more than 1 unit away on this side. But it could also be more than 1 unit away on the other side. Right? Deviation could be on either side. It could be on the left side as well. So we either have to be, let me represent it like this now. We either have to be to the left of 7.2, either in this region or in this region. So probability of x less than 7.2 or probability of x greater than 9.2, we have to find both of these probabilities and then add them up together. And if you think about it, these probabilities are actually going to be both the same because the curve is symmetric. 8.2 is exactly in the middle. 9.2 and 7.2, they have the same distance on both sides, right? So whatever is this area, it's going to be the same area on the other side as well. So you can find one of them and just multiply that by 2, and that will be sufficient. Okay, but I'll show that to you in Z form as well. Let's say if you were to convert both of them to Z, what would they turn out to be? Z less than 7.2 minus the mean, which is 8.2, divided by standard deviation. We found that in the previous part, that was 2.23, plus probability of Z greater than 9.2 minus 8.2 divided by 2.23. Okay, now let's see what this value turns out to be. Z less than what? Minus 1 over 2.23. What's this value? Minus 0.448 to 3 decimal places. Minus 0.448. And if you do the same thing here, that will turn out to be Z greater than plus 0.448. And now if you think of the normal distribution curve, what does the normal distribution curve look like? This is the shape of the curve. What I'll do is I'll make it cleaner. Look cleaner. I will just copy this curve from here. Okay, this is what the normal distribution curve looks like. And now we are saying it's the Z distribution with 0 in the middle. Minus 0.448 is going to be on the left side somewhere. Plus 0.448 is going to be on the right side somewhere. We are looking for these two areas. This area on the left side and this area on the right side. These are the two areas that we're looking for. Because of the symmetry of the curve, these two areas are going to be the same. So what we can do is we can find just any one of them and just multiply that by 2. Okay, any one of them, we can find them and multiply that by 2. So that's the idea. How do we do that now? Let's use the positive value. That's easier to work with. Let's do this. So let's say we're looking for this shaded area. How do we find that? This is not standard form. We can find the area to the left of this, right? That's what the table can give us. So we convert it to 1 minus probability of Z less than 0.448. So whatever is the probability value at this point, since the probability is given for the left part, you subtract from 1 this probability, and that will give you the result. Z value 0.448. Let's see what the probability value turns out to be for this. 0.448. 0.44, that's this, and then 8. That's 29. That will be 6729. Okay. Let me write that down here. 0.6729, and that simplifies to what? 0.3271. That's the probability that we were looking for. And the second part, that's actually just one part of this, right? The right side. The other one is going to be the same as well. This is also going to be 0.3271 using the symmetry of the curve. So we add these two up, and that gives us 0.6542. That's the probability. Is that okay? Any problems with this? Okay, that was the second part. Let's move on now. Let's move on to the third one now. Okay, now the next part, let's try that. So I'm just looking at something. Okay. Now it says, find the probability that of 6 randomly chosen people, more than 2 have visits lasting longer than 10 minutes. Of 6 randomly chosen people, more than 2 have visits lasting longer than 10 minutes. What kind of distribution is that? What kind of distribution is that? That's a binomial distribution. We're talking about 6 people. Out of them, our criteria for success is a visit lasting longer than 10 minutes. So we are saying out of 6, more than 2 people are successful. And the criteria for success is that their visits last longer than 10 minutes. What's the probability for that? Visit lasting less than 10 minutes is 0.79. What would be visit lasting longer than 10 minutes? It would be 1 minus 0.79. That's 0.21. That will be the probability of the visit lasting more than 0.21. So now we can say it's a binomial distribution. We have something repeating. We know the number of our total repetitions, that is 6. We're looking for probability of having a certain number of successes. The probabilities are remaining constant. It satisfies all the conditions of binomial. The key thing that tells you that this is binomial is that you're looking for a probability of getting a certain number of successes, and the probabilities are not changing while there's a repetition. So n is equal to 6, and probability of success, we said that's 0.21. Probability of failure would be 0.79, right? Because this was the criteria for success. Okay. Now, what probability is it that we're looking for? Probability of getting more than 2 successes. More than 2 successes. What does that mean? We want the probability of having more than 2 successes. The formula for binomial, what's that? NCR p raised to power r q raised to power n minus r. Greater than 2 means we have to calculate probabilities for 3, 4, 5, and 6. Or we could do it the other way around, which would just reduce one calculation. If you want, you can do that. You can also do 1 minus probability of x less than or equal to 2. That will also work. You can also try that. 1 minus probability of x equals 0 and x equals 1 and x equals 2. You can subtract these 3 probabilities from 1, and that will give you the same result as well. 1 minus n, which is 6c0 into 0.21 raised to power 0 into 0.79 raised to power 6 minus 0, which is 6, minus 6c1 into 0.21 raised to power 1 into 0.79 raised to power 5 minus 6c2 into P, which is 0.21 raised to power 6, raised to power 2, into Q, which is 0.79 raised to power 6 minus 2, which is 4. And that should give you the result. You can put this on a calculator, see what that gives you. Can somebody please tell me what this result is? Part 3, what do you get from this? If you put this whole thing on a calculator, make sure that you're using brackets properly. You put brackets around this as well. Okay, otherwise sometimes you end up getting wrong values. Sometimes you get an error, but sometimes if it turns out to be integer with this as well, you end up getting wrong values. Always use brackets around the combination function. Okay, otherwise calculator thinks that this one is multiplying with these numbers. Okay, and sometimes it will give you an error, sometimes it will give you some wrong value. So make sure that you're using brackets. So you're telling me that that's 0.112. That's the final answer that we get. Okay. All right, let's move on. That was part 3. Let's look at part 4 now. Part 4 says, find the probability that of 35 randomly chosen people, fewer than 16 have visits lasting longer than 8.2 minutes. Okay, so this is actually that. Okay, so what I'll do is I will explain binomial to normal approximation using this question now. Okay, so this is the next concept that we have. Yes, if in the question they said, instead of deviation by more than 1 minute, if they said it's more than 1 minute above the mean, then yes, you would have only considered x greater than 9.2 in that case. That's correct. But if they just say deviates from the mean by more than 1 minute, that deviation could be on both sides. Okay. All right. Now, this last part is actually something that's the last concept that we had to cover today. But what I'll do is I will explain that concept using this example now. Okay, using this example, since we've reached this point now, let's do that last concept that we have in this topic. And that's called binomial to normal approximation. Let's learn that using this part. It says, find the probability that of 35 randomly chosen people, fewer than 16 have visits lasting less than 8.2 minutes. Now, you see, it looks very similar to what you did in the previous part. So in the previous part, we had 6 randomly chosen people. Now we have 35 randomly chosen people. And we want the probability of having fewer than 16 successes. But the criteria for success now is different. And the criteria for success in this case is visit lasting less than 8.2 minutes. What's the probability of a visit lasting less than 8.2 minutes? 0.5, right? Because 8.2 was the mean. Probability of being on either side of the mean is 0.5. Okay? Probability of being on either side of the mean is 0.5. So the probability of success is 0.5. So the last part here as well, that is a binomial distribution where n is 35, and probability of success is 0.5. Let's write that down here. Now, this is the last concept. Okay, I'll explain this in more detail now because we're doing it the first time. Binomial to normal approximation. This is the last concept that we have in normal distribution. So this is a binomial, and we know that this binomial is such that n is equal to 35. Probability of success is 0.5, and probability of failure is 0.5. Okay. It's a binomial that looks like this. Now, we have to find the probability of having fewer than 16 successes. That's the probability that we're looking for. Probability of x being less than 16. How would you find that in binomial distribution? What do you do for finding such a probability? You find each probability separately, right? So less than 16 would mean you find x equals 0, x equals 1, x equals 2, all the way up to x equals 15. Now, you see, that's a lot of calculations. It is possible, you can do it, but that's going to take a lot of time, right? So that's 16 calculations. It is possible, but that's very inefficient. It's going to take quite long. In the exam, of course, you don't have enough time to spend the whole time on just this question. So this is very inefficient, right? In binomial, if we have a large number of probabilities to calculate like this, it becomes difficult. In geometric, we had a direct formula for inequality as well, right? For binomial, we don't have any such formula. So in binomial, what we have to do is, if we get something like this, we convert this to a normal distribution. We convert this to a normal distribution. The actual distribution is binomial, right? But since we have to do so many calculations, we approximate it as a normal distribution. And this is something that you do a lot in practice. When you go to university, you will find that normal distribution is going to be used in a variety of different contexts. And the reason for that is that any data, if it's very large, you can approximate it as normal distribution. Because of which normal distribution is the most widely used distribution in practice, because whenever you have a large data, whatever the actual distribution is, you can approximate that as a normal distribution. So in our syllabus, we have just one type of approximation, that if we have binomial, we approximate that to a normal distribution. Now, how does this approximation work? This is what we have to find out, right? Probability of x less than 16. Now, for a binomial distribution, the parameters were n35 and p0.5. These were the parameters that we had for binomial distribution. Binomial was described by n and p. What about normal? Is normal also described by those parameters? Normal has different parameters. Normal is described using mean of a distribution, that's mu, and standard deviation. So what we have to do is, if we want to convert it to normal, we find the mean of the distribution and the standard deviation of the distribution. How do we do that? The actual distribution is binomial. Do we know how to find mean of a binomial distribution and standard deviation of a binomial distribution? Do we have a way to do that? Remember the formulas for binomial distribution? For a binomial distribution, mean is given by n times p, and variance is given by npq, right? F1 minus p is the same thing as npq, sq. This can be written as n times p times q. That's the variance. Okay. Now, if this is the variance, what about standard deviation? That will be square root of npq. So what we can do is, from that binomial distribution, we can say, let's find the mean of this distribution and let's find the standard deviation of this distribution. Mean is equal to n times p. So in this case, that ends up being 35 times 0.5, and the mean is 17.5. Okay, what about standard deviation? Standard deviation is going to be given by npq square root. Do not forget the square root. Without the square root, that would be variance. With the square root, this is standard deviation. So we have 35 into 0.5 into 0.5, and square root of that. Standard deviation will turn out to be 8.75 square root of that. You can just leave it like this. That's the standard deviation. Is that okay? So what we get from this is, if there's a binomial distribution with these parameters, we can convert that to a normal distribution that has a mean of 17.5 and it has a standard deviation of square root of 8.75. And these are the two things that we need for normal distribution. Now we can find the probability. What's the probability that we're looking for? The probability that we're looking for is x less than 16. So we could convert this to z and then find the probability. But there's another problem here. And that other problem is that binomial is a discrete distribution. Binomial is a discrete distribution. Normal, on the other hand, is a continuous distribution. Now, how does that make any difference? That makes a difference because in normal, now this is very important to understand, make sure that you're paying attention. In normal distribution, if you had x less than 16, or if you had x less than or equal to 16, would that make any difference? Less than 16 or less than equal to 16, they will both be the same, right? We discussed this in the very first class in normal distribution, that the probability for the equal to case in normal, that is 0. So if it's less than or less than equal to, both of them mean the same thing. Okay, both of them mean the same thing. Same thing. In binomial or any discrete distribution, however, these have different meanings. Less than 16, less than equal to 16, they have different meanings. Because less than 16, that means all the numbers from 0, 1, 2, all the way up to 15, but not 16. And less than equal to 16 means 0, 1, 2, all the way up to 15 and also 16. 16 is also included there. Okay, that's the question. That's the problem. In normal distribution, they would be treated the same way. Now, how does that cause problems? Let's try to understand that now. If you have x less than 16, what that means is the numbers to the left of 16, 0, 1, 2, 3, all the way up to 15, we need to find the probability for all of these numbers. And what are the numbers that we do not want? We do not want 16, 17, 18. These are the numbers that we do not want. So this is the probability that we want. This is the probability that we don't want. Okay. So we want the probability up to and including 15, but we do not want the probability from 16 onward. Now you notice there's a problem. What about this region in the middle? Between 15 and 16, what happens to that? Do we count that or do we not count that? Because in discrete, that area did not used to exist, right? We either had 15 or we had 16. But in normal distribution, we can also have 15.1, 15.2, 15.3, 15.735, 15.9, 15.8. What about all of those values? Do we count them? Do we not count them? How do we decide that? Right? That's a problem now. That the numbers between 15 and 16, because we know that 15 has to be included and 16 does not have to be included. What about the region between them? Okay. In normal distribution, do we count that or not count that? Now, a workaround that we have for this is we say, okay, up to 15, we have to include values. And then from 16 onward, we do not have to include values. What do we do for the middle region? We divide it into half. We divide it into half and we say, okay, let's have a cutoff point in the middle at 15.5. So values that round off to 15, we will count them. Values that round off to 16, we will not count them. So when we consider normal distribution, then instead of finding probability of x less than 16, what we do is we find the probability of x less than 15.5. So that any value that rounds off to 15, we are including that, and any value that does not round off to 15, that rounds off to 16, we are not counting that. So in normal distribution, we would be calculating this probability now, x less than 15.5, rather than x less than 16. This process is called continuity correction. I'll give you more examples of this, but let's complete this question, and then I'll give you more examples of continuity correction, how to decide uh, how whether it's going to become 15.5, 16.5. We will discuss that in a bit more detail. But that's the idea, that it's going to be x less than 15.5 like this. Now, the rest of the process is going to be the same. Now you just find this probability using simple normal distribution. X is less than 15.5. What's the next thing that we used to do for this? We used to convert it to z. So it becomes z less than 15.5 minus the mean, which is 17.5, divided by the standard deviation, which is square root of 8.75. And that gives us probability of z less than minus 2 over this. What's this value? Minus 2 over this. What value do we get? Minus 0.676. Thank you. Minus 0.676. Okay. Nabia, I'll be revisiting that. I'll give you a number of examples of that, of continuity correction. Let's complete this. So let's say we have figured out that this is x less than 15.5 for now. How do we complete this process? We say z is less than this. Okay, now is this the standard form? This is not the standard form. We want z less than positive. So what we do is we think of the normal distribution curve. Let's say this is what the curve looks like. We have 0 in the middle. Z value is negative. We are looking for the area to the left of minus 0.676. That's the area that we want. Now, that's not something that we can find from the table directly. So what we have to do is we have to flip it first of all. We say that area is the same as this area, right? So we can say this is probability of z greater than 0.676. This is still not the standard form. The standard form is z less than a positive number. We have greater than sign, but at least the negative sign, we've gotten rid of that. And now we say, we subtract from 1 the area to the left, subtract from 1 the area to the left of 0.676. So this can be written as 1 minus probability of z less than 0.676. Go to the table, find this probability, and see what that turns out to be. What value do you get corresponding to 0.676 from the table? .67, that's 7486, and then 6. We add 19 to that. Let's write that down here. 7486, add 19 at the end, and that will give us 0.7505. 7505. That's what we're getting here, 0.7505, and the probability therefore turns out to be 0.2495. And that's what we were looking for. That's the probability that we wanted to find. That's binomial to normal approximation. Now, we will discuss a bit more detail of this now, but that's the overall idea. We had a binomial distribution, and it turned out it required too many calculations. So we converted that to normal distribution. How did we do that? We found the mean, mu equals np. Use mu equals np to find the mean. Sigma equals square root of npq to find the standard deviation. So you'll have the standard deviation and the mean. And then whatever probability it is that you have to calculate, you do continuity correction on that. I'll give more examples on that now. You do continuity correction. You convert it to this. And then You just apply normal distribution like you normally do. Convert that to z-value, convert it to standard form, read the value in the table, and you get the result. Okay. Now, let's talk about continuity correction in a bit more detail now, again, using a number of different cases that you could have, because that is something that confuses some people sometimes, but it's a very straightforward way to, there's a very straightforward approach to, approach that. We will discuss that now. Binomial to normal. If in binomial distribution, let's take that same example, x less than 16. If you have something like this in binomial distribution, remember what I said about the problem that we have. The problem is less than 16 means all the numbers from 0, 1, 2, all the way up to 15 should be included. And 16, 17, and all the way up to infinity, they should not be included, right? They should not be included. The region in the middle, that's ambiguous. Should we include that or should we not include that, right? Because less than 16 is basically telling us that 15 number has to be included. In binomial distribution, 15 has to be included and 16 does not have to be included. Now, when we convert that to normal, in normal, we could have decimal values as well, which we could not have in binomial. So in binomial, that was not a problem, that 15 is included and 16 is not included. But when we convert it to normal, in normal distribution, we can also have decimal values. Because of that, we have to be clear what to do about the region in the middle here between 15 and 16. So what we do is we say, let's break this region into two parts at 15.5. The values that round off to 15, that will be values less than 15.5, they will be included. The values that round off to 16, they will not be included. That's the overall idea. Now, how exactly are you going to find it? That's the logic, okay? How would you convert it? This is what you're going to do in the exam. This is x less than 16. You're going to write three numbers. Write three numbers. One less than this number, that's 15. 16. 17. Write that number. One number below that. One number above that. Write these three numbers. Okay? Is 15 included or not? If it's less than 16. Is 15 included in that or not included? 15 is included. This is included. What about 16? Is 16 included? Is 16 included? 16 is not included. 17 is also not included. Now, where the decision is changing, as in 15 is included, 16 is not included, in normal distribution, you will use the midpoint of these values. You will say this becomes probability of x less than 15.5. In normal distribution, you would use 15.5 here. Okay. Now compare that with if you had x less than or equal to 16 here. If instead of less than 16, what if you had less than or equal to 16? How do you think about this now? Again, 16 is the number. You consider 16. You consider one number less than that and one number more than that. And now you think of this. Is 15 going to be included in less than equal to 16? Is 15 included? Yes. Does 16 satisfy that condition? Less than equal to 16? Yes, 16 also satisfies the condition. Does 17 satisfy the condition? 17 does not satisfy the condition. So 17 is not included. Between the tick and the cross, what number do you have in the middle here? 16.5. When you convert it to normal, this would be x less than 16.5 now. Okay, that's the probability that you would find in normal distribution. Let's take another example. Let's say you had probability of x greater than 44. How would you think of this? Write down the number 44. Write down one number less than that, one number more than that. Okay. Now, greater than 44. Which of these numbers satisfy this condition? Is 43 greater than 44? No. Is 44 greater than 44? No. 45? Yes. Where is the decision changing? So, between the tick and cross, this is 44.5. In normal distribution, this probability would become x greater than 44.5. Okay. And then what if you had probability of x greater than or equal to 57, for instance? What about this? Again, you write down 57, write down one number less than that, write down one number above that. Is 56 included in this interval? No. 57? Yes. 58? Yes. Between the tick and the cross, you have 56.5 here. In normal distribution, you would consider x greater than 56.5. That's the probability that you would calculate in normal distribution. This is called continuity correction. That's the way to do it. Does this make sense now? Does this make sense now? Let me know if there's any problem here now. Any problems here? Can I get more responses? I know you've been studying math since morning, but still. Okay, good. So that's the idea of continuity correction. So what do we do now? In binomial to normal approximation, we find the mean, we find the standard deviation, and then we do continuity correction to get that. And to get the probability that we have to find in that context. Okay. Now, can we always do this? Can we always approximate? Could we do this approximation in the previous example as well? We had n equal to 6. We could say, okay, that's too much calculation. 3 probabilities that we have to find, right? That's too many. Why not just approximate it as normal? Can we always do it? There's a condition for it. Okay. There's a condition for using binomial to normal approximation. What is that condition? Let me write that down here. Remember I said in practice, what happens is if the data is very large, you can convert that to a normal distribution. Now, how do you define large, right? What's the cutoff for being large? The convention that we use in Cambridge is this. Conditions for using binomial to normal approximation. You cannot always do this approximation. There's some condition for this. The conditions are that NP should be greater than 5. NP should be greater than 5. And NQ, that should also be greater than 5. Both of these numbers, both of them have to be greater than 5. If both are greater than 5, then we can use approximation. Otherwise, we cannot. Okay. If both of these numbers are greater than 5, then we can use approximation. Otherwise, we cannot use approximation. So in part C, in the third part, for instance, N was 6. Probability of success was 0.21. N into P, what would that be? That would be 6 into 0.21, and that will be something very small, 1.26. That's less than 5. You could not use approximation in this case. right? The data is very small for the approximation to give you a reasonable result. Okay, if the data is large, then the approximation is going to be fairly accurate, right? It's going to be very close to the actual answer. It's still an approximation. That's why we call it an approximation. But the larger the data is, the larger the value of NP and the value of NQ, the better the approximation is going to be. These are the conditions that we've got for using binomial to normal approximation. Does this make sense? Right? Okay, so now this is the last concept that we've got. Third type of questions that you will get, binomial to normal approximation. So what would happen would be, you would have a binomial distribution, which would have some value for n, some value for p, some value for q, and you would have to convert that to normal distribution. What you would do would be, you would find the mean, find the standard deviation using these formulas. Once you've done that, you will do continuity correction. And then you find the probability using normal distribution like you normally do. Okay? What are the conditions? NP and NQ, both of them should be greater than 5. This is the condition for using this approximation. But in terms of concept, yes, that was the last thing that we had. So now, what I'll do is, I'll have a look. I'll quickly do a couple of more questions. Okay, I'm sorry for that, for extending the class a bit. But I want to do a couple of more difficult questions so we can, wrap this up today. If you still have more questions, of course, we can discuss them. But let's do a couple more today so that tomorrow we can focus on linear transformation and diagrams then. All right. If anyone of you has any other question that you want to ask about, you can do that right now. Otherwise, I'll choose some myself. Okay. What I'll do is I will search for an approximation question quickly. And then we do a relatively more difficult one on normal. And then we could end with that. In fact, this looks like a good one. 39. How many of you have attempted this question already? Question number 39. Question 39. How many of you have attempted this? Question 39. Was it straightforward? Okay. So what I'll do then is, let's do 42 right now. Because we just did approximation. Let's do one question on this. And then I'll find one that's relatively more difficult. This is 42 from the worksheet. In Scotland in November, on average, 80% of days are cloudy. Assume that the weather on any one day is independent of the weather on other days. Use a normal approximation to find the probability of there being fewer than 25 cloudy days in Scotland in November. Now, the last example that we did, they did not tell us that we had to use approximation. We had to figure that out ourselves, right? So if we have a large number of probability calculations to do, that means a large number of probability calculations in binomial distribution, that means you have to use approximation. But mostly what happens is they tell you in the question as well. Whenever in stats, whenever in S1, you have a problem in which they talk about approximation. The only possibility that you have in your syllabus is binomial to normal approximation, right? That's the only approximation that you have in your syllabus. So whenever you see the word approximation, what that means is they're essentially telling you that the original distribution is binomial and you have to approximate it as normal, right? So approximation word basically tells you that the original distribution is binomial and you have to convert it to normal. Okay, so in this case they're saying use the normal approximation to find the probability of there being fewer than 25 cloudy days. So what is it that we're focusing on? Cloudy days. We can say that's the criteria for success. We want 25 successes out of 30 days. All right. What's the probability of success? 80% days are cloudy. So probability of a day being cloudy, that's 0.8. So we can say this is a binomial distribution. This is a binomial distribution with n equal to 30. We're talking about 30 days. So n equals 30. Probability of success. Success is defined as a day being cloudy. So that's 0.8. Probability of failure, that would be 0.2. What we're looking for is probability of there being less than 25 cloudy days. That's the probability that we want to find out. Okay. Now, less than 25, that means 0, 1, 2, 3, 4, 5, 6, all the way up to 24. You have to find all of these probabilities. That's too much calculation. If you do 1 minus something, then you would have to find probability of 25, 26, 27, 28, 29, 30. Subtract these 6 probabilities from 1, right? That could work, right? That's still doable. But they have told you that you should be using normal approximation. Now, how do you use approximation? We've got formulas for mean and standard deviation. What's the mean formula? What's the mean formula? Mean formula is n times p. So it becomes 30 times 0.8, which is 24, right? Mean equals 24. And then standard deviation is npq square root. That would become 30 into 0.8 into 0.2. And then square root of that. What does that turn out to be? 24 into 0.2. That is 24 over 5, which is 4.8. Square root. That's the standard deviation. So we've got the mean and we've got the standard deviation in the normal form. Okay. Mean is 24 and standard deviation is this. Now we have to do continuity correction. We have to convert this to a probability for normal distribution. Now it's either going to be 25.5 or 24.5, right? What is it going to be? Less than 24.5 or 25.5? What do you think? When we do continuity correction, is it 24.5 or 25.5? How do we think about this? We think of 3 numbers: 25, 1 number to the left of it, 1 number to the right of it. Is 24 included? Yes. 25? No. 26? No. So we have to be between these 2 numbers. That's 24.5. Yes, so that's correct. That's x less than 24.5. That is what we would be using here. And now we just find this probability that's going to be converted to z. First of all, z less than 24.5 minus 24 divided by square root of 4.8. And that will give you some z value. What does this turn out to be? Z less than 0.5 divided by square root of 4.8. What's this? (0.228). Thank you. That's 0.228. And now, is this the standard form? This is z less than a positive number. We could find this probability directly from the table, right? We don't have to convert it anyway. It's z less than positive. It satisfies that condition. 0.228. 0.22, that gives you this. And then 8 here. That's this number, 31. 0.5871. Let me just get rid of the rest of these numbers. Okay, 0.5871, and then you have to add 31 at the end. On your calculator, if you wanted to do it, you would do something like this: 5871 plus 31. That gives you 5902. You write 5902 here, and you put a decimal in the beginning, 0.5902. Okay, that's what you have, 0.5902. You write that here, 0.5902. And that's it. That's the probability that we were looking for. Okay, that's how this approximation is going to be used. Now, what does the second part say? Give a reason why the use of a normal approximation is justified. Remember, we have conditions for using normal distribution. We have conditions for using normal distribution. It does not always work. The condition is NP should be greater than 5, and NQ should be greater than 5. Now, this is not sufficient. This is not sufficient. You can't just write it down as it is. You have to show how the conditions are met in this particular context. So you have to show the examiner that N in this case was 30. Probability of success was 0.8. This gives us 24 greater than 5. That condition is met. So you have to show this working. Similarly, N30 into Q, which is 0.2, that's greater than 5. That means 6 is greater than 5. This is also met. And now we say, since both conditions are met, that means that the use of this approximation is justified. Okay, if even one of these conditions was not met, then the approximation would not be accurate. We would not use that. If this condition is not met, then it would not be justified to use it. Make sense? All right. Okay, now let's do one more question at least. Let me see if I can find a relatively more difficult one. I don't watch football. I just don't like it. Binomial nomination. Those of you who have practiced, tell me the most difficult question that we can do right now. कोई था ही नहीं मुश्किल. Okay. I want to use do one of them that says something like this: where probability of some number being within a certain number of standard deviations. So statements like that. I can't find that right now. Okay, maybe in that other worksheet we would have one. I want to sleep right now as well. So I'm not sure if I'm searching hard enough. Recent topicals, S1. Normal distribution worksheet. Let's see if search works on this. Yeah, let's find that. That's too many. Okay, let's just do this one last question then. This is from November 18th. Yeah, let's just do this one last question, okay, and then we end with this. So there's one small thing that I want to explain using this one, and that meaning of z value, okay, and that will be very helpful in some cases to do some questions more efficiently. I'll explain what I mean by that. So this is the question that I want to do right now. It's question number 33 from the second worksheet. Remember when we started normal distribution, we talked about the z values. Now notice something about z values, because that's going to be very helpful in doing some questions more efficiently. So I wrote down some values of x. And for each of those values of x, I showed you how to calculate z, right? What the z values were for both of them, for all of them, using this formula. Now notice something. X is a variable that has a mean of 60 and it has a standard deviation of 12. Mean is 60, standard deviation is 12. Now look at the z values that you're getting here. When x is 60, what's the z value? Z value is 0, because 60 was the mean for the z distribution. 0 is the mean, so 60 corresponds to 0. Okay. What about 48? This is giving us a value of -1. What does -1 mean? 60 minus 12. If we subtract 12 from 60, what does that give us? That gives us 48. What's 12? 12 is the standard deviation of this data. So if we subtract one standard deviation from the mean, we get 48. The z value that we get from this is because of that -1. Okay, now notice this pattern now. This is 84. 60 was the mean. Standard deviation was 12. If you want to make 60, convert 60 to 84, how many standard deviations do we have to add to it? Standard deviation is 12, right? How many 12s do you have to add to 60 to get 84? We have to add 2 12s to it, 2 standard deviations. You see the value of z? That's 2. Okay. Similarly, the 1.5, for example, 78. We have to go from 60 to 78. How many 12s do you have to add to get 78? 1.5 12s, right? So this value is 1.5. So the z value has a specific meaning. This has a specific meaning, and that is, let me write that down here. The z value It basically represents the number of standard deviations you are above or below the mean. The number of standard deviations, the value is a value of X is above or below the mean value. That's the interpretation of the Z value. So -1 means 48 is one standard deviation below the mean. 2 means 84 is two standard deviations above the mean. 1.5 means 78 is 1.5 standard deviations above the mean. 90 means 2.5 means that 90 is 2.5 standard deviations above the mean. So Z value tells you the number of standard deviations a value is above or below the mean. Okay. Now, why is that useful? Let's look at this question. We have a variable X, which represents time. And it's the time for which students use the games machine on any given day. It's normally distributed. The mean of this data is 3.24, and the standard deviation is 0.96. That's the standard deviation. Let's look at the last part. We'll do the first two parts as well, but since we've done something just very fresh, let's look at the last part, 3. It says, find the probability. I'm doing the third part first, and then I'll do the first two parts as well. Find the probability that the number of hours which a randomly chosen student uses the games machine in a day is within 1.5 standard deviations of the mean. Within 1.5 standard deviations of the mean. Now, what would be the normal way of doing this? You would say, okay, mean is 3.24. Let's add to that 1.5 standard deviations, 1.5 into 0.96. What would you get from that? 1.5 into 0.96. You add that number to 3.24. And on the right side, you get 4.68. On the left side, you subtract 1.5 standard deviations, and that will give you something 1.5 into 0.96. (3.24 minus 1.5 into 0.96), and that's giving me 1.8. You would say normally that probability of X being between these two numbers, that's what you're looking for, right? That would be within 1.5 standard deviations. And then you would convert it to Z values. You would say 1.8 minus the mean, which is 3.24, divided by the standard deviation, that's 0.96, and then Z, and then that's less than 4.68 minus 3.24 divided by the standard deviation, which is 0.96, and then you get some Z values from this. You can skip all of this. You can skip all of this working, and you can directly say, since we are saying we have to be within one standard deviation of the mean, within 1.5 standard deviation of the mean, Z value tells us the number of standard deviations you are away from the mean. In a Z distribution, what's the mean? Mean is at 0. So within 1.5 standard deviation, what does that mean? You have to be between minus 1.5 and plus 1.5. And that's it. You directly have Z values. You don't do any of those calculations. It doesn't even matter what X was. Eventually, after doing all of this working, you would have gotten the same thing. this would be minus 1.5 here, and this would be plus 1.5. No matter what the original mean was, what the original standard deviation was, eventually you would always get this. So when they talk about number of standard deviations, you can directly write z values in that case. You don't have to do all of that calculation. You can say z is between minus 1.5 and plus 1.5. And now this is the probability that you can find. It's a standard case that we have done before. You think of the normal distribution curve. What does that look like? This is the normal distribution curve. Let's draw that. What is it that we are looking for here? We want the area between minus 1.5 and plus 1.5. That's what we want. Between minus 1.5 and plus 1.5. This is what we're looking for. How do you find this area? You can use this symmetry. You can use the symmetry. How can you use the symmetry? You can say, let's find just this part. Can you find this part? We will just multiply that by 2 then. Okay, I'll repeat that. Let me just complete this. I'll repeat that again. So what we do is we find this one part and then we'll just multiply that by 2. So let's just focus on this one part, the right part. What's that going to be? Probability of z being less than 1.5, right? Minus this region, we know that is 0.5. So this minus 0.5, that will give you 1/2 of that shaded region, right? You will get this shaded region from that. Z less than 1.5. Subtract from that. On the left side, we have 0.5 probability. We can just get rid of that probability. So I'll just get rid of this shading so it becomes a bit easier to understand. What I'm doing is I'm saying, let's find this area. Okay. And then I'll just multiply that by 2. How do you find this area? I'm saying, let's find the area to the left of 1.5, subtract from that 0.5, and you would get that area. Then you just multiply that whole number by 2. And that will give you that probability. Let's see what that turns out to be. Z less than 1.5. What's the probability for that? 1.5. This is 0.9332. That's what we write here. 0.9332 minus 0.5, and that's going to give you the result. You can see what that is. 0.4332 times 2, that will be 0.8664. 0.8664. That's the probability that we are looking for. So we could just do this much working. We could skip all of this. We could skip all of this. Okay. Now, why can we do this? Let me repeat that again. Ibrahim, you thought that it's not that important, so you stopped paying attention when I told you what the z value means. How do you understand z values? Z value represents the number of standard deviations, and x value is above or below the mean. Okay. So for example, -1 z value, that means you are 1 standard deviation below the mean. 2 means you're 2 standard deviations above the mean. 1.5 means you're 1.5 standard deviations above the mean. So z value basically tells you the number of standard deviations you are above or below the mean. Okay. So if it's a positive value, that many standard deviations above the mean. If it's a negative value, you're below the mean by that many standard deviations. Now this question says, you have to be within 1.5 standard deviation. Within 1.5 standard deviation. What does that mean? we eventually have to convert everything to z, right? So we can think of z directly. In the middle, we have the mean of z, that's 0. So 1.5 standard deviations below the mean, that would be minus 1.5. 1.5 standard deviations above the mean, that will be plus 1.5. You have to be between these two numbers, and that's it. So z is between minus 1.5 and plus 1.5. So whenever they say you have to be a certain number of standard deviations above the mean, a certain number of standard deviations below the mean, whenever they talk about number of standard deviations, you can just write the probability in terms of z directly without having to do any calculation. You can write this down in terms of z directly. Does that make sense? All right. Okay, so that was one point that I wanted to make using this example. Now let's actually just do the other parts quickly and then we end for today. A calculator can only be used for verification, and that's just an alternative for using the table. Okay, it's not that it'll do the whole question and the thinking for you. It'll think everything for you and give you the answer. That's not how calculator is going to work. Calculator can only help you replace, or not even replace, it can only help you verify the value that you're reading from the table. Reading the table is not that difficult. You still have to be able to read the table because you have to show the examiner that you are reading value from the table. Okay, a calculator can sometimes give you more accurate value, and the table does not even have that much accuracy. So examiner would know that you have not used the table, and for some reason they are still stuck in the past and they want you to be able to read this table. They don't want you to use a calculator. So that's the way it is. Okay, the only thing that you can do using a verification is using a calculator is you can verify the value that you've read from the table. I think that's a waste of time because it's so straightforward. uh, Reading the value from the table, you don't really need to spend time verifying that, right? You would have probably more important things to do in the paper rather than verifying this table value. So I would not really recommend that you spend too much time on that. Okay. All right. Now let's have a look at the first and second parts. We have the mean given and we have the standard deviation given. Now this should be quick. On how many days of the year would you expect a randomly chosen student to use a games machine for less than 4 hours? What we do is we find the probability that on one particular day, what's the probability that a student that on one particular day a student uses less than 4 hours using the games machine for less than 4 hours? Can we find this probability for one day? Let's do that first. Convert it to z. It's not simple normal distribution. So it becomes 4 minus the mean, which is 3.24, divided by the standard deviation, which is 0.96. And that will give you some value. What do you get from this? What's this? 0.792. Is this the standard form? It is the standard form. It's z less than a positive value. So we can use the table directly. We don't have to change it anyway. 0.792. Remember, it's the z value. In your table, look for 0.792. The z value of 0.792, 0.792. That's what you're looking for. This is the number that we get here. This is 6. So 0.7852, add 6 at the end, it becomes 7858. Okay. Point 7858. That's the probability that we're getting from the table. Now that we have the probability, this is the probability that on one day, a randomly chosen student uses a games machine for less than 4 hours. What about 365 days? On how many days would you expect him or her to use the games machine for less than 4 hours out of 365 days, you just multiply this by 365 because this is for one particular day. For 365 days, you multiply this by 365. 365 into 0.7858. What do you get from this? 286.8. But remember, we're talking about number of days. They can never be in decimals. So it has to be an integer. You have to round it off to 287. If you write a decimal, you will lose a mark for that. Okay? You have to write an integer here. We're talking about number of days. All right? We're talking about number of days. So yeah, that's what we get. That's the first part, really straightforward. Now the second part is inverse normal because we have a probability given. That's x greater than k equals 0.2. That's the last part that we're doing for today. And then we end. Probability of x greater than k, that is equal to 0.2. This is the probability that we're given. What we do is we first of all convert it to z. We have probability given. We have something missing in the data. So this is inverse normal. We write this in z form first of all. We say, okay, probability of z greater than some value, that is equal to 0.2. And now we need to decide whether this is whether z is positive or negative. How do we do that? We think of the normal distribution curve. The area to the right side, is that smaller or bigger? That's smaller than 0.5. Wherever the value is, to the right of that, you should have less area, smaller area. So if we place z here, on the right side, you have bigger area. That's not what we want. If we place z here, on the right side, you have less area. We have smaller area. That's what we want. That means z is supposed to be a positive value. So that's what we understand. Z is positive. Okay, now z is positive. And we know that this area here, this is 0.2. This area is 0.2. Is that the standard form? Z greater than something? It's not the standard form. We can say if the area to the right of right of that value is 0.2, what about the area to the left of that value? That would be 0.8. So we can say this implies that z less than the positive value of z, that is actually 0.8. This is something that we can find from the table now, because this is standard form, z less than a positive number. Go to the table, find the z value corresponding to this probability. 0.8 is probability, remember. Go to the table, find 0.8 probability here. 0.800, that's the probability, right? This is the number that we see, the smaller number than 0.8. 0.84, that's the z value. But then how much more do we have to add at the end? We have to add 5 more. So we have 2 here, 842. 0.842, that's the z value that we've got. So the z value, therefore, that turns out to be 0.842. And since we know it's a positive value, we keep it positive. And now we can just input values in the formula. Z equals x minus mu over sigma. What does that give us? 0.842. That equals x, which is k, minus the mean, which is what? What's the mean? 3.24, divided by standard deviation, which was 0.96. And that will give you the value for k. You can see what that turns out to be. What's the value of k? What value of k do we get? 4.05. Thank you. K equals 4.05. That is our final answer. That's what we were looking for. That was inverse normal. And that's it on normal distribution. I hope that makes sense and that was helpful. If you still have more questions now, you can either ask them in an extra class that we might have. Because tomorrow now, we are going to do representation of data, linear transformation, and the diagrams. Okay, so that in terms of concepts, we get done with it. Then we will have at least one more class on Friday, in which we do some practice on representation of data. And then it depends on you guys. If you think you need more practice in anything, we could schedule another one at some point as well. But in terms of concepts, we should be done tomorrow, inshallah. We've done sufficient practice in normal distribution as well now, although you need to do much more than this. And if you have problems, you can let me know, both in that live class that we would have, an extra class that we might have, or on WhatsApp. You can send your question on the WhatsApp group as well. But make sure that you do practice. Do not leave that for later. Otherwise, you will end up forgetting these concepts that you've learned. Okay, so practice right away. Spend this weekend on completing S1, all the assigned questions and more from normal distribution and representation of data. Okay, all right. So that's it for today. So those of you who want to leave, you're free to leave. Now, if you have any specific questions, you can let me know. Allah Hafiz, everyone. I'm sorry for delaying these classes until this late, but we're almost done now with our syllabus. And these nighttime classes are going to end, inshallah. Allah Hafiz. Yes, Nabia and Ibrahim, you can go ahead with your questions.
Assalamu alaikum, sir.
Walaikum assalam.
So, sir, I had a question regarding the symmetry of the normal distribution curve. So, if the question is z less than 0 or maybe z greater than 0, then the probability is 0.5, right?
Yes.
So, but if z is between -1 and +1, the probability should be 1/3, because I feel like if we distribute the curve symmetrically, like divide it in 6 parts, then -1, between -1 and +1, it's 2 out of 6.
Okay, so there are two problems with that logic. Number one, it looks like, so do you think that it's meeting the x-axis here? Is that what you were assuming? That it's touching the x-axis here?
Yes, sir. I'm assuming that at one side it's +3 and at the other side it's -3.
Okay, so that's the first problem. That assumption is wrong, because it looks like it's meeting the x-axis. In actual, this normal distribution is basically making an asymptote here. So it keeps going on like this on the right side and on the left side. It's not meeting the x-axis. It's like a zoomed out version. If you zoom in, then it makes an asymptote. Okay, so it goes towards positive infinity and negative infinity. That's the first problem. And even if it was to meet at -3 and +3, still that would not make sense, because close to the mean we have bigger area. As we go away from the mean, the areas become smaller. These are smaller areas. This is even smaller. So we can't divide those probabilities equally, right? So there's symmetry, but that symmetry is that these two probabilities are equal to each other. This yellow probability and this blue probability, they are equal to each other. Or all the probability on the left side, that's equal to probability on the right side. That does not mean that for any given interval, the probability is going to be the same. Okay?
Yes, sir. Thank you, sir.
Okay. Yes, Ibrahim.
Assalamu alaikum, sir.
Walaikum assalam.
Sir, can you please go to question number 29 worksheet, sir?
जी ये वाला
हाँ जी सर। सर इसके अंदर मैंने पूछना था, जैसे अभी इन्होंने यहाँ पर 2μ लिखा हुआ है, इस 2μ के ऊपर हम फार्मूला लगा के इसको पहले कन्वर्ट करेंगे, फिर फर्दर प्रोबेबिलिटी करेंगे उसके ऊपर।
2μ के ऊपर फॉर्मूला लगा के इसको पहले तो z में कन्वर्ट करें ना। सो
हाँ, मतलब इसको कन्वर्ट करना पड़ेगा ना, फिर ही लगेगा, आगे सॉल्व होगा।
बिल्कुल। So you get z less than 2μ minus mu divided by sigma, right? That will give you probability of z less than mu over sigma, right? This is the probability that you have to find out. Now you are given, now you can't find this probability, right? Because this is mu and sigma, these are not numbers. So you would say, using this equation, let's find sigma in terms of mu or mu in terms of sigma. So for example, you could say mu is equal to 5 over 3 sigma. Can you do that? Right? Mu is equal to 5 over 3 sigma. Now you can input that value here. You can say this becomes z less than 5 over 3 sigma divided by sigma. So that just leaves you with probability of z less than 1.667.
Yes, sir. All
So
right.
that becomes a number then, right?
All right. Okay, then. Got it.
Okay. That's it?
Yes, that's it.
Okay, then
Thank you.
कल फिर हम linear transformation करेंगे इंशाल्लाह और graphs करेंगे. That's it for today. I'll see you again tomorrow. Allah Hafiz.
Allah Hafiz.